I'm Michael. Today I'm going to be talking about Terraform. Just for a little bit of context, my name is Michael. I'm Heap on Twitter if you want to say nice things about the talk. If you want to say bad things, don't put that on the internet. And I'm a developer advocate at a company called Nexmo. You might be able to tell by branding. We do SMS, voice, communications in general. If you want to talk about that later, come and find me. And for those of you that don't know Adam, sat in the front, he lives in Bristol. We work together. And he told me he's happy to come and sit at your company and help you implement Nexmo any day you like. But this isn't about that. This is about a previous life that I had. And in a previous life, I wasn't a developer advocate. I ran an operations team. And when I joined, it was wonderful because there was no infrastructure. It was entirely greenfield. It was a startup. So I did what anyone would do. I started adding things. Just one machine, a Jenkins server. And then we said, oh, well and good, now we need to build on the Mac as well as Linux. So I had another Jenkins server. Now some backups and some test machines for developers, and then a demo environment for business development. And before I knew it, we had half a dozen different environments. QA, staging, biz dev, you name it, we had it. I thought there has to be a better way to manage this rather than just going in and clicking around and creating machines. And that's when I found Terraform. Now, for those of you that don't know Terraform, it's from an awesome company called HashiCorp. You might know some of the other products, Consul, Vagrant. If anyone uses Vagrant, they made that, Vault. All of these work really well together. We'll mention a few a little bit later on. But we're just going to focus on Terraform for the beginning. Terraform is a tool for defining your infrastructure as code. And for years, getting a new server meant walking down to a data center, racking it, plugging it all in, and bringing it online. But over the last couple of years, with the introduction of cloud providers, it's becoming easier and easier to get a server. Instead of having a 6-week lead time, all you have to do is log in, click around on the console, and suddenly you have a virtual server. It was revolutionary. Instead of waiting weeks, we were waiting minutes. And this is fine if you're just creating 1 or 2 servers. But how about 10? How about 100? 1,000? How can you guarantee that they're all launched with the same settings? The short answer is you don't. You can't at that scale. We needed a way to declare what we want the machines to look like and just have a computer create it for us, because computers are great at doing the same thing over and over. And this isn't a new idea. We've been doing it for years with tools such as Puppet or Chef for configuring servers. Terraform provides us with the same ability, but for creating the servers rather than configuring them. And it's really, really simple. We'll come back to this in a little while, but that is all you need to create an Amazon EC2 instance. So a little bit of background on Terraform. It was created in May 2014, and since then there have been 89 releases. 0.10.4 was the most recent. They tend to get maybe 3 releases a month out now, which is pretty good. And of those 89 releases, there are 1,129 individual contributors. It's not just one company that owns it, it really is a community effort. And it covers all the big cloud providers, as well as lots of others. There are currently 68 providers, covering cloud providers, domain registrars, DNS providers, CDNs. And if they don't work with an API that you want, you just write a plugin for it. It's all plugin driven, people can contribute whatever they want. At its core, Terraform is a tool that allows us to define infrastructure. It allows us to define what we need in a declarative manner, and it takes care of working with all the different APIs to get us what we need. But, and I can't stress this enough, it is not an abstraction layer. Every API has its own resources within Terraform. You can't just say, give me a machine in AWS, and then tomorrow say, give me a machine in Microsoft Azure cloud with the same resource, you would have to re-implement that. All the clouds out there are sufficiently different that trying to normalize them, well, you just lose functionality on each cloud. And just to drive the point home, Terraform is declarative. It's like JSON or YAML. There are no if statements, there are no loops. It's a configuration format, and we trust Terraform to work out what to do when we define our desired state. So, what's the plan? I'm going to start off with the basics, getting Terraform installed, creating our first plan. Then we'll cover some techniques to reduce copy-paste, followed by how to provision the machines that you've created. Then we'll briefly cover some of the things I wish I'd known when I started out with Terraform. Sound good? Cool. Installing Terraform. Now, I don't know if any of you have got experience with things like Chef and trying to get the right Ruby gems installed and things like that. For Terraform, it's written in Go. You download the binary, you make sure it's in your path. That's it. There's no missing dependency pane. It's all compiled into one. Just download and run. Really simple. And that gives you the Terraform command line. And there are lots of different commands in there. I think there's something like 20. But 90% of the time, you only need these three. Terraform plan will tell you what Terraform plans to do. Terraform apply makes it do it. And Terraform destroy, well, the clue's in the name, it deletes everything. So, our first plan. We've got Terraform installed. We want to create an EC2 instance. First thing we need to do is configure our system with AWS credentials so that Terraform can access the API. You can do this a couple of ways. You can provide them as environment variables. You can provide them directly to Terraform, or it will read your AWS credentials file. I like using the AWS credentials file because that's where the AWS CLI looks, where lots of other tools look. So I just define them once and everything looks there. Then we'll create a directory, go into it, and just create a file called main.tf. That's the convention. Your entry point is always main.tf, and that comes from the fact that it's written in Go. To get started with Terraform, you just tell it what provider you want to use, and in this case, which region you want to use it with. Like I said, you can provide authentication details at this point, but I'm not because it's in my AWS credentials file. Once you've got a provider, we need to tell it that we want an instance. And we saw this at the beginning. There's not much there. We tell it we want an AWS instance. We're going to call it web, that's our internal name. It uses the Ubuntu image. It's a micro instance. And we're going to call it Hello World. And that's all there is to it. Just provider, resource, save it, and we can run Terraform plan. Once we have a definition, we need to apply it to our AWS account. So if we run plan, it talks to the AWS API and works out what's up there, compares it to what we said we want, and works out the diff. And in this case, it's comparing what's up there, which is nothing, with our local state, which is that we want to create an AWS instance. And it's told us that's what it's going to do. This hasn't actually done anything. This is just an FYI saying this is what I want to do. It's not until you run Terraform apply that it actually goes off and it talks to the create APIs. And this takes, well, this took 22 seconds to create an instance. When we go to the console, we see it there. It says hello world, that's what we called it. And that is your first Terraform plan. Like, there's not much to it, but it creates an instance. And if we go through again and run Terraform plan, it talks to the AWS APIs, works out that we've got an instance there. It's called hello world. It's got the right AMI. It's the right size. There are no changes to make. And it tells us that. One instance is okay, like it's a start, but new requirements have come in. Like, we're going to get loads of traffic tomorrow, we need more. One instance isn't enough, we need 3. All we need to do is add this line. We just tell Terraform, instead of having 1, implicitly it has count equals 1 internally, but we can override it. And the next time we run Terraform plan, it's clever enough to detect that we already have 1 instance, and it just wants to add 2 more, bringing our total to 3. Once we run Terraform apply and actually make these changes, we'll have 3 instances running instead of 1. That's good, but it's giving us another issue. Like, we've got 3 instances. How do we point traffic at all 3? Instead of giving each one an IP address and doing that through DNS, we can put a load balancer in front, and Terraform can help us with that as well. So this time we're using the AWS ELB resource. We give it a name, details of what port to listen on, what protocol to use. And this is all documented. The Terraform documentation is fantastic. It tells you what's required, what's optional, it gives examples. But there's one line in here that doesn't look quite like the rest. It's this one. Everything else is just hard-coded. This is the syntax for referencing other resources in Terraform. We don't know which instances we need to register with the load balancer because they're dynamically created. But we can reference them saying we had an AWS instance. That was the resource that we used. We called it web. The bit after that is a little bit weird. The store is because we've got multiple instances. So at that point, it would normally be the instance ID. But here we're just saying, get me all of them. And I want to get the ID out of that. When Terraform runs, it will pull in the data from the APIs, and it will interpolate that so that the instance IDs that it created are passed to the load balancer. And just like before, we run plan to see what's going to happen. We run apply to make the changes, and then we profit because everyone can get to all 3 instances and the company's happy. Or they would be, but although we created the load balancer, like, we didn't actually do anything with it. Like, we don't know what its IP address is. We could go into the console and click around and pull it out, but the whole idea of this is to not do anything manually. Which takes us nicely on to the next section, which is outputs. And an output is a special kind of resource which can store the value of any variable available to Terraform. So we create output.tf, again, just a convention. So now we've got main.tf and output.tf. We say create me an output called lb_DNS, and the value of this is the AWS ELB resource. We called it LB, and we want its DNS name. See how all of the resources refer to each other? And then we run Terraform refresh. And I didn't mention this one earlier. I said plan, apply, destroy. Refresh is automatically called when you call apply. It's just the bit that does the fetch all the data from the AWS API, compare it to my local state. It doesn't actually do anything. It's just a comparison. But when we run it, suddenly we see this output appear at the bottom. And it's given us the public DNS name for our load balancer. Or if you wanted to feed that into another script, you can just run Terraform output-JSON, because all of that is cached, and it gives it you in JSON format. It's fantastic for chaining things together. And then the last thing to do is just to destroy everything that we created, because Terraform is pretty good at telling you what it's going to do. So we run Terraform destroy. It says, I'm going to destroy things, just in case you didn't realize. Here's what I found. Are you sure you want to do it? And it's not like you just hit Y and it goes, or Y enter. You have to type yes, like full yes, I realize what I'm doing here. And once that's deleted, we can run Terraform apply again, and it will create all 3 instances and a load balancer. And we'll do that in under a minute. This is it actually running. What's quite nice about Terraform is it realizes that all of the instances are disconnected, so it can do them in parallel. It doesn't do one, then wait, then do the next, then wait. It builds up a dependency graph based on the references, like the load balancer references the instances, builds that up internally and says, okay, then I create all the instances first. Once I have all the instances, I can create the load balancer. So it doesn't matter whether you're creating one instance or 1,000 instances, it's going to finish in roughly the same time. So here, it took 40 seconds, well, 2 finished within 29 seconds, 1 finished after 40, load balancer, and done, and it output the load balancer DNS at the end. That's exactly what we want. We never have to go into the console again, set things up by hand. We have this definition, doesn't matter how many times we destroy it, we just run Terraform apply and it recreates. Woo! Come on, you can do it. We just created our first Terraform plan. How many of you had heard of Terraform before today? Okay. How many of you think you could give it a go now? That's what I like to see. It's really not that hard. If you, yes?
Do you need to have the AWS utilities not installed it, or it's all self-contained?
All self-contained. Yep. So that's something I missed actually. So when you create your folder and you define a provider, you actually have to run Terraform in it, and that will scan through, see all the providers that your Terraform code has used, and download all the plugins. So it's all self-contained, and actually the versions of plugins are per project. So you don't have to have one global install. You can use one version of the AWS SDK in one project, one with another. So that was pretty good. 3 instances, 1 load balancer. But it was kind of like my first Terraform plan. In this section, we're going to introduce variables. We've kind of used them, where we used AWS ELB and AWS instance. Those were variables, but these are ones that I want to set. And at the minute, our instance definition looks like this. We want to rename it to be something a little bit more sensible than Hello World. The web servers, let's rename it to Web. But then all 3 instances will be called Web. How do we know which is which? Wouldn't it be good if they could have unique names? And thankfully, Terraform has us covered here as well. Anytime you specify a count, a magical variable named count appears. And this will create 3 instances called Web 0, Web 1, and Web 2. You can do all kinds of crazy things with this count index, and some of the functions like lookups from another list. So you can define your machine names in one list, then use the count index to extract the names from the list. I don't have that in here because it is a little bit crazy. But if you want to learn more about all of the functions that you can apply with count, talk to me afterwards. So this will create Web 0, Web 1, Web 2. 0 indexed. And whilst we're editing the tags, let's just add another one to specify what environment this belongs to, because people are going to see this, they're going to love it, and they're going to want their own. So this is ours, this is dev. We'll add the same tag to our load balancer. And I've just noticed that we're copying and pasting. Like, what happens if we think, oh, actually, dev's a bad name. Like, we're one dev team, and we have 10 dev teams. Like, which team does it belong to? We'd have to go through and change our instance and our load balancer. Unless we add a variable. And the environment is a prime candidate to be extracted. Create variables.tf. Those are the only 3. Main.tf, output.tf, and variables.tf. And create it with this content. And this defines a variable, gives it a type. There are only 3 types for variables. There's strings, maps, and lists. There are no booleans, no integers. Those are just strings. You can use the word true and the word false, but internally they get converted to 1 and 0. So we go back in and we change it out. And variables are prefixed with this void dot. So just at the bottom, we've got it there. And in our ELB, we've got it there. I've also added it to the load balancer name here to make it unique. Because otherwise AWS will complain if I tried to create more of them. There's a couple of ways to specify values for variables through the environment. TF for then your variable name. You can specify it on the command line when you run Terraform, or you can put it in this TF voice file, which is kind of like an ini format, just key value. Alternatively, you can set a default when you define the variable, or Terraform will prompt you for a value when it runs. Come on. Woo! Now your plan file is nice and dry. You're not repeating yourself. You've got one instance definition with the count, and you've got your environment name as a variable. And we're doing pretty good. But then actually people have caught on saying, well, how come that team's got their own test environment? Like, can we have one of those? Then someone comes to you and says, come on, they're asking, can they have their own copy? You say, yeah, I can do that. How would I do that? Would I just copy and paste the instances and change the variable name? Then would I have two variables in one? Or like, how would I do this? Would I have it in separate folders? But then when you start changing things to get out of sync, if we were building an application, like we'd write a function here, wouldn't we? And then we just call the function whatever it needed to be called. And Terraform has a similar concept. It calls them modules. Modules are pretty simple. When I first started out, they confused me a lot because I felt like I was missing something. But to create a module, all you do is you take your Terraform plan and you put it in a folder. That's it. Your plan is now a module. I mean, we have to write another plan that uses that module now. But that's all encapsulated. It's in the module called demo. And this is what our new plan would look like. We're running a module. We provide it with a source, and that can be a local path. It can be a Git URL. The Git URL can have branch references, SHA-1 references, tag references, so you can version them that way. And this is where you now provide values for your variables. So here we're creating an environment with that definition called dev. And the other team wanted one, so we just include it again. But instead of environment dev, we say environment others. And that's all. Now we don't have to copy and paste. We don't have to keep things in sync. We have a reusable definition for an environment that we just call whenever someone else needs one. But we have lost something here. Remember that DNS name for the load balancer? Well, Terraform only passes that one level up because it'd be called LBDNS, but which instance of this module does that refer to now? Like, we don't know which one, so it passes it up once, and we have to define new outputs. Dev LB and other LB. And again, it's a variable. We say we're referencing a module called dev. We want to read LBDNS out of that. Anytime we run apply or refresh, the DNS values will be returned. Yes! We just created the module. Like I told you, when I first looked at this, I felt like I was missing something. I was like, it can't just be copying it into a folder. But it really is. Don't overdo this though, because when you find that you open up a plan file and say, okay, cool, this calls a module, you click into it, say, what does this do? Oh, this calls a module, this calls a module, and a module, and it's modules all the way down. It's an absolute nightmare. There are pros and cons to making modules for everything. Things like encapsulating the AWS instance so that you always use a consistent AMI. That feels like a good idea, right? But then you find that you need to slightly tweak one of them here and one of them there. Then you have to define more variables to pass in to tweak it. And suddenly it becomes a God module where it does everything that the AWS instance module does, just with an additional layer of indirection. So my personal feeling on this is define an environment and then wrap that, because that is the unit that you want to replicate. So that is the only point at which I will create a module. Whilst that will work, what I showed you is not recommended. And what I mean by that is just copying and pasting from dev to others. Because what happens is suddenly those two environments are linked because they share the same TF state file, they're in the same AWS account. If you're doing this with dev and production, a change to your dev environment could wipe out production. That's not what you want. So what I do is I create one plan file per environment. So I have a folder called dev and put main.tf in there, and have a folder called others and put main.tf in there. Let them have their own TF state files. If you can, use different AWS accounts, different credentials, keep them as far away from each other as possible. So we've got all these boxes. We've got 3 boxes. We've got a load balancer. We can send traffic to them, but they don't actually do anything. This is the danger. Like, we can get empty boxes, but then we still have to log in and configure them by hand, or remember to run Ansible against them ourselves. Wouldn't it be nice if Terraform could do that for us? Terraform does have this concept of provisioners. They are one of the more neglected areas, but it is still in there. And they kind of give you just enough rope to hang yourself with. I like Ansible. And here we use the local exec provisioner, which lets us run any command we like on our local machine. And we provide the same command that we run by hand, just Ansible playbook, what user, what key to use, what playbook to run. The only thing that we do get is this self.public IP, which references the IP address of the instance. So it automatically grabs that data, passes it in, and runs Ansible. This could be run a shell script that you've got. It could do anything. Like, people could write a provision that runs rm/rf/, and when you run that Terraform plan, it wipes out all your files. Like, this is what I mean by it gives you enough rope to hang yourself. It's just running local commands. But on the plus side, that gives you flexibility, because you can do exactly what you want with it. The alternative is that you provide commands to run on the box. And if you do this, you have to provide connection details. It's SSH, what user it's going as, what the password is. You can use key files and things like that. And then you just provide it with a list of commands to run. So here our app is packaged up. So we install Nginx in our app, and then we restart Nginx. And those will run on the remote machine. There is a third one that I haven't put in here because it wouldn't fit on the slide, and that's the chef one. The OpsWorks, the guy, they're called Chef now though. I think they're renamed. The Chef team use Terraform quite a lot. They're quite involved. And there is a Chef provisioner, and that will automatically register a node with your Chef client, bootstrap it, all kinds of things. So there is the capability to do the deep integrations, but it's not there for a lot of them. If you want to write a plugin for Puppet or Ansible or Salt, whatever you want, do it, contribute it. I'm sure they'd love to have it. But until then, we can just turn off the screen. Been talking too long. You can just fall back to local exec and do it that way. While Terraform looks pretty great, there's still one massive hole in it at the moment. And that's that your TF state file is on your local machine. Only the person running Terraform has a copy of the state at that point in time. So if you're working with a co-worker and they have an outdated state file, They don't know all of those resources exist, so when they run Terraform, bad things are going to happen. We struggled with this for a long time. When I started using Terraform, this was the only way, and we actually ended up putting it in Jenkins. And we just said the CI system owns the state file, never run it on your local machine. Thankfully, there are now better options. As of 0.10, we have official remote support. You might see things like TerraGrunt, which is a wrapper for Terraform, which used to use DynamoDB for remote state. But you don't need that anymore. Terraform has it built in as of 0.10. All you need to do is configure your plan to use it, and it can use Amazon S3, it can use Console, also from HashiCorp. You can use Terraform Enterprise, which I haven't used yet, but it does look pretty good. The idea is that you write your plan and you push it up to them. And it's a central place to see the diffs, to run it, to record state changes. You get the state changes going all the way back. If you are using Amazon S3, enable bucket versioning, and you get the same. I do want to look at Terraform Enterprise, because although I imagine it's pretty pricey, it's basically GitHub for Terraform. I mean, if you're betting your infrastructure on Terraform, like, what's a couple of grand in licensing fees? Like, if all of your infrastructure disappears, how much is that going to cost? I've got notes here. It's got the multiply, it's got the run history, state diff. It's got everything. This is an advanced subject, but I figured I should mention it as it can catch people out. And it's to do with lifecycle management. So I mentioned our load balancer and 3 instances earlier. If we change the AMI, say new Ubuntu came out, 17.10's out, let's upgrade to that. In AWS, that's not an update, that's a new resource. It's going to delete your old machines and create new ones in their place. Which is fine, because then provisioners kick in and they install everything and everyone's happy. Until Terraform is really clever and realizes, actually I can parallelize this. I can delete those whilst I'm creating those. And you end up with a load balancer that has no instances registered against it. And there's nothing to handle the traffic. And that's where create before destroy comes in. If you set this lifecycle, Terraform will always create the instances, run any health checks, make sure they pass, register it with the ELB, and then delete the old instances. It does mean for a little while you might get requests to the new and the old version, but that's okay. Your applications can handle that, right? Now this has to be put on every resource all the way down. So if you put it on, say the instance, any networks that's attached to, any VPCs that's attached to, like any of its dependencies also need this setting. Otherwise, Terraform will get into a circular loop where it's saying, I can't delete that. I can't delete the VPC because I can't delete the instance, and I can't delete the instance till I delete the VPC and create a new one. So yeah, lifecycle all the way down. Which brings us on to our final item, immutable infrastructure. The idea behind immutable infrastructure is that once a machine is started, it never changes. This works perfectly with Terraform, as all we have to do is change the AMI ID and run Terraform apply. Because of our lifecycle, create before destroy, it will create with a new image, spin it up, delete the old ones. There's no need to worry about provisioning or anything like that, because the image is pre-baked with everything that we need. This has the added ability of being able to use AWS's auto-scaling groups, because at the minute, if we use an ASG and Amazon create new instances because ours are very heavily loaded, they'll come up but they won't actually do anything because Amazon doesn't know about our provisioning kit. You thought this was a talk on Terraform. It was all just a big lead up to selling you Packer. Yet another HashiCorp tool. It's wonderful. You still use Ansible or Puppet or Chef, but the idea is that you run it once and then you disable it. You run it as part of your build pipeline. It provisions all your config files, applications, like it normally would when you're provisioning a server. Then it takes a snapshot, then takes that image and gives it to you. And then you upload that to AWS. And then when you launch an EC2 instance, instead of providing the base Ubuntu AMI, you give it your own ID. And then that instance comes up and suddenly your application's already there, it's already running. And then the ASG kicks in and says, we need more servers. It uses your AMI, your application's already there. Immutable infrastructure is a whole other talk on its own. If you're interested, find me afterwards, we can chat about it. And we do have time for some bonus content. I don't go into depth. There's a lot here that I couldn't talk about. But I'll just let you know what the headlines are so that you can go away and look at it yourself. Did you know that Terraform can import and manage your existing infrastructure as well? Like you're already using AWS, you don't want to destroy all that and create it. Terraform import ID. At the moment, it doesn't automatically generate a plan. It just imports it into the state file. It automatically generating the plan is on the roadmap. So you need to make sure that you write the AWS instance definition to match what you've got. Otherwise, once it's in the state file, it will delete it. So, do you know you can mix and match providers in a single plan? Like we were just using AWS all the way through. Is your app on Heroku and your DNS on DN Simple? Fine. Or maybe you're running on AWS, Microsoft came along and said, hey, how would you like £250,000 worth of credit on Azure to move? You say, I'd love to, but I can't move everything at once. Terraform doesn't care. It's just another provider. You start defining Azure resources in your plan. It spins them up. You can decrease the count on AWS, increase it on Azure. You can do it piece by piece. You can configure how Terraform runs in your plan file too. You can choose your remote state provider, S3, console. You can enforce minimum Terraform versions if you know that the behavior in 0.8 wasn't quite what we wanted, so let's enforce 0.9 or above. Configure all that in your plan file. It's not additional config anywhere. There are tons of functions for all kinds of variable manipulation and data lookup. There aren't actually over 9,000, there are 59. It feels like there are over 9,000. Chomp, coalesce, element, file, all kinds of things. Coalesce is pretty cool. It just takes a list of values and the first non-empty one it uses. You can use that for setting quite clever defaults. File is quite good when you have to upload an SSH key and you don't want to copy and paste that into your plan file. Use the file function to read it off disk at runtime. Push that up as a string. It has read-only data providers. Instead of hard-coding an AMI ID, why not just search for the latest Ubuntu 17.04 64-bit image from Canonical? Use that. Because they release point updates all the time. I'm not sure I want to do that. I like knowing what I'm running. But let's flip it around. What about when you're using Packer? You upload your own AMIs. You very rarely want to be running an old version. You always want the most recent image that you pushed up. So why not search for your own ID? You can override small parts of a plan using Terraform's override functionality. So I keep talking about this main outputs variables.tf. That's a convention. Terraform does not care. You could call it banana.tf and it would still read it. It just looks for anything .tf, merges them all into one. Sorry, it appends them all into one. Important word there. If you define override.tf, however, that will merge it. So instead of making everything configurable, just in case you want to change things, if you want to change things to test, just use an override. You can override that hard-coded AMI ID that's 4 modules deep that you don't want to expose. Just make sure that you use the right resource, give it the right name, stick it in override.tf, And once Terraform's finished building up its internal plan, it will apply yours on top, and then it will make the changes. And of course, I left the most important thing to last, testing. Testing's pretty tough at the moment, I'm not going to lie. And a lot of the efforts around it are focused on asserting that infrastructure is in the state that you need after it's been created. That can get a little bit expensive, like if you're spinning up machines and you've got a big infrastructure. If you're doing it through a CI job and it's creating 4,000 servers a day, even if they're only running for a minute or two, that's going to add up. There are efforts to try and work with the Terraform plan file, so you can generate a plan and then write tests against that. That's looking quite promising, but there's nothing solid there yet. So really, your only options are AWS spec, which was the original. It wasn't written for Terraform, it was just written for AWS, and you can assert that different VPCs exist, instances are running with the correct IMI, things like that. Or if you're not using AWS, InSpec from the Chef team is pretty good. It supports AWS, it also supports Microsoft's Azure Cloud, Google Cloud Engine, that kind of thing. If you're on AWS, I'd probably use AWS spec, if not, use InSpec. Which brings us to the end of the talk. Now, we've covered quite a lot in a relatively short time. I'm mheap on Twitter. Feel free to get in contact if you've got any questions, if there's something that I didn't explain quite correctly. I'd love to hear that, actually, because this is the first time this talk's been given. In fact, about 3 hours ago, this talk wasn't finished. So it probably has rough edges. Please do tell me, don't be nice. Like, this needs to get better. This have 45 minutes, which means we've got 3 minutes for questions if anyone has any. Yep.
So with immutable architecture, how do you do apt-get upgrade? You know, an apt-get update, because once you've run it, you're now in a different...
You don't run it on the server. You run that as part of your CI process. It's a new image that you then ship.
So let's say I do it every week, even though none of my code's changed every week. For security, when I say, you know.
Yep. As soon as something changes on the server, it's not the same install anymore. It doesn't matter whether that's your application code, whether it's a dependency. You build a new image, you ship that.
So basically, even after my active development's done, if I go down this route, then every week I have to send out a new image just to get the latest security updates.
Yeah. The benefit of that is you know exactly what's running. People, if they went in and changed one file by hand or anything like that, that gets wiped out. It has a nice side effect, actually, which I forgot to mention, which is when you're working with configuration management tools, it's really strange. You're running Ansible, you add a user, you add John Smith. John Smith leaves the company. The answer is not to delete his entry from Ansible, it's to add a remove. And that catches a lot of people out. And then John's account just sits on the server forever. It's a lot of additional overhead, like cognitive overhead. To get rid of John, I have to add something. With immutable infrastructure, you just delete his name, and the next time the image is built, because it starts from nothing, John isn't there anymore. So there are a lot of benefits. There are a lot of negatives as well. But like I said, immutable infrastructure is a whole talk on its own, but we can chat about that later if you want. One more. Don't be shy, in the back. Go on.
So you mentioned that modules get used for environments. Then you said if you want to break out the environments and push them up into another fold, what actually should go in a module, if not a separate environment or a wrapper for an instance?
So there's two things with environments. So one is the module that creates it. So I used to have a company full module, which will be the full shebang, like redundancy, 3 database servers for quorum, everything. And that was a module. And then I had a separate folder, which was the plan file for production. And all it did was reference that module and fill in some variables. And I had another one for staging, which used the same one because we wanted it to be identical, but that was in a separate folder to production. So it was a separate TF state, separate credentials, separate AWS organization, but it still pointed at the same module. because we wanted them to be in sync with each other.
Okay, so you use the file system methods to basically go up and then into a common module called the two environments.
In the example I was, in practice, we didn't use the file system. We actually thread the git URL and you went and checked that out at a specific revision. The downside with using file system is if you're testing with staging and you accidentally run it with production, production is going to get all your changes. Whereas if you use a git URL and a revision, production is pinned until you actively go in and update the version of the module that it references. Cool, that's me done. Find me later if anyone's got any questions or tweet me on Twitter. And please do leave feedback. Thank you.